class, I'm Demaris Lopez-Carrasco, and I'll be presenting on Down syndrome. Here is an example of a karyotype. As you can see, the 21st chromosome has 3 copies of that chromosome instead of the usual 2. A karyotype is just one of the many diagnosis mechanisms. There are also amniocentesis, chronic villus sampling, sonograms, serum screening tests, and some options have a risk for causing miscarriage, so it's important to take that into consideration for parents who have high-risk pregnancies and they still don't want to put the fetus in any more risk than the fetus is already in. Statistically, there are 6,000 babies born annually with Down syndrome just in the US, and there are 1 in 700 American births annually. The symptoms of Down syndrome include a flattened face, almond-shaped eyes slanting upward, a short neck, small ears, white spots in the iris, small hands and feet, poor muscle tone and loose joints, short stature, hearing loss, sleep apnea, heart defects, mental disability, developmental delay, a protruding tongue, long and short-term memory problems, a crease across the hand palm, a groove between the first and second toes, impulsive behavior, and a short attention span. In terms of discovery, there have been centuries-old mythologies in literature. It used to be called Mongoloid, which is obviously insulting. When Mongolia joined the World Health Organization in '65 and asked to change the word, so therefore the term is a combination of both racism and ableism. English physician John Langdon Downes published descriptions of Down syndrome in 1866, and so he became the father of this genetic disease. The French physician Jerome Lejeune characterized Down syndrome as a chromosomal condition in '56. So both of these men are in one corner, but then in the other corner, I have a little girl with Turner syndrome here. This photograph is an example of people with Down syndrome in the arts, particularly in photography. Causes of Down syndrome is that maternal age is the only known factor. An additional copy of the 21st chromosome can be traced back to either parent with genetic testing. This usually occurs from non-disjunction in cellular division. So before conception, a pair of 21st chromosomes fails to separate in either the sperm or egg. In embryo development, the extra chromosome is replicated in every cell the body has. Called trisomy 21, this occurs in 95% of cases, so it's the majority. Mosaicism is when there's a mixture of cells without trisomy 21 and others with it. As the least common form, it's only 1% of cases. Translocation is where the 21st chromosome breaks off and attaches to another chromosome. So testing is done to determine if this is inherited or not, because it can be. It's possible for the parent to have 45 chromosomes because 2 are still together, but remain healthy anyway and have no symptoms. Genetic counseling can tell which parent carries translocation. There's still no significant difference between those with non-disjunction and those with translocation because the symptoms are still the same. Just to clarify, when sperm and egg are formed and they replicate, the chromosomes usually split in half. So one half goes to one cell and the other half goes to a different cell. However, in non-disjunction, the chromosomes stay together and go into the same cell instead. In translocation, the chromosome segments break off and switch places, so every chromosome will contain half of the other chromosome in that case. Here is a physical description of what translocation looks like. In terms of treatment, genetic diseases right now are incurable, but there is educational, physical, speech, emotional, behavioral, and occupational therapy that can really benefit patients. Social workers, physicians, surgeries, assistive devices, medications, and supplements can all improve their standard of living. In function, chromosome 21 is the smallest, containing about 48 million base pairs and consisting of 1.5 to 2% of our total DNA and 200 to 300 genes that instruct protein production. These proteins are expressed in the brain through biochemical and cellular pathways. In inheritance, only 1% of cases are inherited. A third of translocation downs is inherited, but most are sporadic, as a lot of genetic illnesses are, where the parents aren't carriers, they don't have a family history, and still they end up having a child with a genetic disorder. Once parents have a baby with trisomy 21, the chances of a second infant with the condition is 1 in 100 until they're 40. If the father is the translocation carrier, recurrence is 3%, but it's 10 to 15% when the mother is. Most men with Down syndrome can't have kids, but some can, so it requires a sperm count test to see if they are or aren't fertile in their individual case. Women with Down syndrome are able to have kids. They have a 35 to 50% chance of passing it on to their kids. In the family case study here that I've invented, Luz and Marco marry and instantly try for a pregnancy. Luz and her relatives don't carry any genetic abnormalities. Marco doesn't know it, but his family does have a tendency for translocations. He, his father, and grandfather all have translocations in different chromosomes. They've had balanced translocations and no illnesses themselves, but proper distribution of chromosomes in the cells have now become unbalanced in the sperm. Now, one of these unbalanced sperm has fertilized one of Luz's eggs, resulting in the 21st chromosome breaking off and attaching to another chromosome. Even from the ultrasounds, doctors can tell the child will require medical treatment once born. Their child is born with translocation Down syndrome. The doctor recommends genetic counseling after examining the karyotype, because that's when they found out translocation is the culprit, and now they can trace it back to either Luz or Marco, and at that point they can get counseling on their family planning and on their risks for having another child with a translocation. Here is a physical representation of what translocation Downs looks like. As you can see in the 21st chromosome, they still have the regular 2, but there's a third copy of the 21st chromosome attached to another one, the 14th chromosome in this case. In terms of future treatment, gene therapy can only add genetic material to replace faulty or missing genes to restore protein function. The new material goes into RNA polymerase and instructs protein production. Therefore, this wouldn't work in the case of extra chromosomes, since material would need to be removed, not added. It would have a better potential for monosomy conditions in which the chromosomes are either missing or to replace faulty genes. The main limitation is that every cell in the body is affected by a missing or extra chromosome, so changing every single cell and making sure they won't divide with the same condition is a Herculean feat. Recombinant proteins increase protein production. This would be better for handling possible symptoms of Down syndrome like diabetes with assisting insulin production, as people with Downs are at a greater risk of developing diabetes, and this might actually be helpful in Alzheimer's treatments for dementia, because Down's syndrome patients are at an increased risk for developing that too once they grow old. However, I want to pose an ethical question. Do people with Down syndrome even want to be cured? What about their choice in the matter? Would it be best to treat their symptoms and ensure that they have access to the resources they need to lead fulfilling, quality lives as independently as they're able to? What would society lose without genetic diversity and without the contributions of people with genetic disorders? And here is a list of my sources.